Hey guys, good morning. We're going to talk today about quadratic relations and different ways to distinguish the difference between things that you have learned, so looking at linear graphs, and moving into our new unit, which is focusing on quadratic relation graphs and just getting used to the different key characteristics. So as a focus, excuse me, I'm going to mirror back and forth between what you do know or what you should know by now, because in grade 9 the heart and soul and the focus of grade 9 is to focus on linear graphs, and we even spent a bit of time in February and March with our time together earlier this year on what linear graphs should look like in terms of graphing them in y equals mx plus b, and then we're going to transform that knowledge into what quadratics is. Okay, so the three main ways to determine if it's linear versus quadratic, there's actually three things that I'll be focusing on today. Okay, the first thing I want us to focus on is it's look in an equation form. Okay, so you'll notice for your linear graphs, we have y equals mx plus b, where x has an exponent of 1. Okay, we don't see it, but it is there. And for our quadratic relations, we have one example of what a quadratic equation can look like, and that's y equals ax squared plus bx plus c, where you'll notice that your exponent of x, or your degree of x, is 2. Now remember, you're going to be acknowledging the highest exponent of x, which is what a degree is. A degree takes a look at all the terms in your polynomial and uncovers what the highest exponent is. So although there is an x to the power of 1 for b to the power of x, we're more focused and interested in the highest exponent, which is x squared. Okay? We'll talk more about this later. The second key idea is looking at its graph. So you'll notice for linear graphs, the main focus is, does it look like a straight line? So in this case in our graph, obviously it does. If we were to take a look at the equation of the graph that we have right here, we would say it has a y-intercept at positive 3. And if we were to calculate its rise over run, we can take any two good points, up 1 over 1, up 1 over 1. So that means that m is 1. So if we were to put that information together, we could even make an equation in our linear form of y equals 1x plus 3. Okay, we did that earlier in the year. But you know what? I'm just talking about its visual form, right? So in its visual form, if we consider this graph, we know that's a line because it increases. Other lines that we have focused on are decreasing lines that go downwards. Those both represent linear graphs. Okay? For quadratics, the key thing is it looks like a U-shaped graph. And this U-shaped graph is called a parabola. Okay? So for a parabola, it is a U-shaped graph that either opens up or down. The third characteristic that I'm going to introduce and talk to you about today is also your first difference tables. Okay, so in a nutshell, we could have been given this. You were taught this in grade 9 and we read a little bit in grade 10, a table of values chart, and a way to determine if it's linear is to see how it increases or decreases. So if we take a look, remember in your difference of y's, it would be 2 take away 1, which is 1, 3 take away 2, which is 1, 4 take away 3, which is 1, 5 take away 4, which is 1. So you'll notice they all increase by the same value. You can also consider your change of x, right? So delta y over delta x, and they also increase by 1. This means that this, in fact, is a linear graph. And it's a linear graph because the first differences are constant. Okay. Now, we're going to observe for the table to the right, we have here a table of values, okay, and we would actually apply the same thing. We would calculate our first differences like we did to the left. And we would say, okay, what's 2 take away 12? That's negative 10. Negative 4 take away 2, that's negative 6. Negative 6 take away negative 4, that's negative 2. And then negative 4 take away negative 6. And you'll notice that that's positive 2. Now, everything that we've calculated in our difference of y's are all different numbers. So this is not constant first differences. So meaning that this can't be linear. So typically last year you would have just stopped and said, okay, it's nonlinear because we know linear graphs have to have the same constant first differences. This year what we're going to do is we're actually going to take your first differences and calculate something called your second differences. And your second differences take your first differences and actually just find the finite differences between them. So what that means is in our first point, we're going to take negative 6, subtract negative 10. Remember, 2 negatives make a positive, so we actually have plus 4. We're going to go to the next one where we take negative 2, take away negative 6, and you get plus 4. Positive 2, take away negative 2, and you get plus 4. So now you see I get plus 4 all the way down. So my second differences are a constant, and this is what makes it quadratic. Okay? If your first differences are the same, it's definitely linear. If your second differences are the same, then it's definitely quadratic. So in a nutshell, here are your 3 key main ideas. You can tell a quadratic relation is a quadratic relation amongst 3 different ways. So visually, by its looks, in a graph form, it is a U-shaped graph called a parabola. So if you see a U, it's a parabola, meaning it's quadratic. If you see a line, it's linear, therefore not quadratic. For your equation, there's always an x squared term. This is very important in a quadratic equation. So for example, we have 5x squared as an example of an equation. We have y equals 2x minus 3 squared plus 1. That's very important. And then we have y equals 2x squared minus 1x plus 5. Okay, so in those 3 different equations, they all represent quadratic relations. The last way to determine if it's quadratic is looking at the table of values. So like the work we did up here. In a table of values, if your second differences are the same, if they are constant, it is quadratic. That's the main thing. You have to go through your first differences, obviously first, to determine if they're constant or not. We did a bit of this on the whiteboard using those arrows, right? However, you should also recall that if your first differences are the same, then it's linear. Any of these 3 ways, depending on the information that is given to you, all represent quadratic relation key points. Okay, so all of these all allude to this idea that if any of these factors exist, it is a quadratic relation. So what I'm going to do is I'm going to briefly talk in each section about the information that I just discussed. Okay, and there's going to be examples that we can look at together. Okay, so again, linear graphs, they are called lines. They can increase or decrease. Right, so we see that in a grid form. We see that in a potential real-life example form. Okay, now how does that differ from quadratic graphs? Well, we can see in our 3 different examples, quadratic graphs are called parabolas. They are U-shaped graphs, and they either open up or down. So just to determine which ones open up or down, this opens up. It kind of looks like a smiley face when it opens up. Right? And this one opens down. Right? When you're sad, you typically frown, so you open down. Okay. Now, what's important also in recognizing opening up and down is that all the parabolas actually form 2 directions. So on the far left, if we are going from left to right in terms of analyzing its direction, coming from the top left, we are actually coming down. We then hit this minimum point, and all of a sudden we change directions and we start going back up again. This happens in all cases of parabolas, whether they open up or down. They change direction after they hit a certain point, and that point is going to be very important. We're going to talk later on this week. It's called a vertex, and that vertex is your changing point where it changes direction. In our middle graph, we have a soccer player, and you'll notice after the ball makes contact with their foot, it obviously reaches the highest point, or in this case, a maximum point. Then it returns back to the ground, again changing direction. In your last graph here, we have a roller coaster, right? So if you've been on a roller coaster at Canada's Wonderland or any other theme park, you'll notice that this direction of going up and down and anything that's U-shaped is something that does obviously change directions, right? So we go up, we get the thrill, we hit a maximum height, and then we go back down. And then we might repeat that or take a different route. Okay? The main thing is our U-shaped graph, again, is called a parabola, and it gives us this basic parabola of y equals x squared. Okay? Now, sometimes we have parabolas that might change or alter, where it's not always going to be that parent graph. But for now, let's just focus on the fact that all of these graphs, if it looks like a U, it's going to be quadratic because they are parabolas. Okay, so as a self-quiz, if you want to pause for a sec, which of the following is a parabola? Okay, the correct answer is our fourth one. The first one is linear, and the other three are different types of functions that you would learn in higher levels of math, but definitely the only quadratic that is present out of those five is that fourth one. Okay, so the next two actually have real life situation scenarios, so I want you to take a minute and just look at these diagrams. Okay, so if you want to look at it on your PDF, and then pause the video so that you can actually process and think what or which graphs depict the height of a bungee jumper and which graph depicts the throwing of a football. Okay, so hopefully you've had a second to think about that. If you want to continue thinking about it, feel free to pause the video. For the bungee jumpers, okay, so think about people who are really into the thrill of, you know, going to extreme heights and are into extreme sports. But basically when you start as a bungee jumper, you want to either climb up to an accelerated height. So you would not obviously start at ground level before your jump or before your descent. You would start at a certain height. Okay, so right now, A, D, and even B are possible. Okay, but generally what happens is when you jump, you're going to hit a max height, and then you're going to go back to the ground where you started. Okay, so in terms of which depict the height of a bungee jumper, because you're going to have that little leap, B is not going to be an option. Okay, so I'm going to leave it between A and D. Unless you're a pro leaper, I'm going to say D is going to be a little trickier because you can see the distance across to get to that maximum height. But again, this is just for discussion, right? It's quite a bit of a leap, even though we don't have numbers, but if we were to throw in, you know, meters, that's quite a bit of distance, right? Compared to here, that seems a little bit more ideal, okay? If I was going to pick one, I would definitely go with A. However, open to interpretation could also be D. But again, that's looking real professional if you can leap that much horizontally and then descend back on your way down. Okay? All right. Which graph depicts the throwing of a football? Okay, so if we were to consider a person who throws a football, okay, so using your dominant arm, the football would eventually reach a max height and then eventually fall back to the ground. Okay, so with that graph would definitely be either this one, and sure, I'll leave this as an option. Okay, now typically when you throw a football, you're throwing it from your hand, right? So meaning you're already a certain height above the ground. So we're not starting at ground level, okay? And we're definitely not throwing the ball below ground level unless we're throwing it underwater and it somehow resurfaces up. But I think in this case, I would actually go with D. Okay, for distance. A is a little too short of a flight. If you're throwing a football, you definitely can have quite some distance. Okay, now most real-life parabola questions have this U-shaped graph that opens downwards. Okay, now we'll just focus on the equation part. So for the equation part, which of the following is a quadratic equation? So remember, we're looking for x squared examples. So where we see x squared is here. 2 to the x is not 1 because the exponent has to be x squared. Okay, so any of these, that one has x cubed, so that's not what we're looking for. And the first one on the second row is linear. So everything that I've circled so far are all quadratic relations because they have a second degree polynomial, which means it has a term with x squared as your highest degree. Okay, so now we'll talk about the table of values. Now, I actually went into quite some detail in the above page when we were looking basically up here at what same first differences and what same second differences actually means. But let's do an example to see what that actually looks like if we were doing it from scratch. Okay, so we're going to focus on your change of y's. Okay, here, yes, they all go up by 2. Okay, so we're good. You got to make sure your x's always go up by the same amount, but we're more concerned with the activity in the y. So my little trick is so that you don't get mixed up with what number gets subtracted from, the other number, I always start at the very bottom and then work my way up. So it's going to be 49, take away 25, 25 take away 9, 9 take away 1, 1 take away 1, 1 take away 9, and then 9 take away 25. Okay, and we're going to find our first differences to begin with. Okay, so 49 take away 25 should be 4 take away 2 is 2, 9 take away 5 is 4. 25 take away 9 should be 16. 9 take away 1 should be 8. 1 take away 1 should be 0. 1 take away 9 should be negative 8. Oops. And 9 take away 25 should be negative 25, 34. Okay. So now we're going to take our differences and we're actually going to calculate our second differences. What am I thinking? It's early. That said negative 9. Okay, so 9 take away 25, negative 16. Perfect. Okay, so now we're going to take our second differences and we're going to do the same thing where we start at the bottom. So 24 take away 16, 16 take away 8, 8 take away 0, 0 take away negative 8, negative 8 take away negative 16. And what you'll notice for each one, it equals 8. Okay, so we would say this would be a quadratic relation because your second differences are constant. Okay, and even if you wanted to take a second to see and ensure that what you have is actually a quadratic graph, so does it look like a U-shaped graph, you can always graph the points that are in your XY table of values. And see if you have a U-shaped graph. And you do. Okay? All right. We'll go through B very quickly. This one's a little bit easier to determine because you can visually see that all the x's go up by 1 and your y's. 11 minus 10 is 1. 10 minus 9 is 1. 9 minus 8 is 1. So you already catch the drift. Okay, so therefore, this is a linear relation because your first differences are constant. Okay? So now in terms of putting it all together, so this is going to be your work. Okay, so for the following graphs, please complete graphing for it. So for the linear graph, group 1, there should be a review of what we did earlier in the year. For the graphs on the right, group 2, please use the table of values and substitute values of x in for y and solve. You can always use the desmos.com graphing that I showed you. You could put it into a table of values, or you can just put in these actual equations into Desmos. Okay, and just work on graphing them. Okay, if you want to use the table of values, you can. Okay, so basically I can show you this really quickly. This is going to be our equation, so it's y equals x squared. So we're going to take all of these x values and sub them in. So this is like negative 3 squared, which is 9. This is like negative 2 squared, which is 4. Okay, and then put in all those values and see if you can solve them. You're going to graph them. Obviously, I know not all of you have a printer at home, so if you want to graph it on Desmos, that's why that's an option for you. Or if you have graph paper at home, you can always graph these 6 graphs. Okay. There's also going to be an investigation that I'm going to post as a separate PDF. Okay, so please complete any 2. You'll see there's different investigations. Again, no submission is required, but I just want you to go through them. So if you want to use Desmos for those as well, or if you're able to do it on paper, it shouldn't take you too much time. Okay, so hopefully this video was clear on how to determine the difference between linear and quadratics. Again, please